Let's talk about climbing grades, specifically why they are important and how they could be improved. Climbing grades are essential for customers to track their progress over time, as well as avoiding injury. Improperly graded or inconsistent grades are a hassle at best and hazardous at worst for the climber. A better grading system will attract more climbers to your gym and increase the overall quality of your service. Note that solutions such as giving grades a range like V1 to V2 or V3 to V4, as shown here, don't work well since those ranges are still based off of subjective measurements. Instead, I am proposing to create an objective way of measuring a climb's grade. Now, there are a handful of previous studies that have attempted the same thing as me here. After some digging, I found these two were the main ones. So starting with the study from the University of Twente in the Netherlands. So what they did was they collected data on climbs using what they called CRDL notation, which is a complicated way of categorizing both climbing holds and the moves between said holds. So for example, if we scroll up, you can see, they have like right hand to jug or left reach to jug, right match, etc. So it was a complicated system that was admittedly very versatile, but hard to use, I would imagine. And what they did was they built a machine learning model that attempts to categorize climbs as either easy or hard. So they kind of simplified it down from the standard, for example, V0, V1, V2, etc. And what they found was their best model was around 64% accurate, which at a 95% confidence interval was actually better than just random chance, which would be 50%. But, even what they called just a simple classifier where they only guessed easy every single time would actually yield an accuracy of 62%, given that the distributions are a little bit uneven. So in the end, their model was not as accurate as they would hope, and they cited concerns with their data quality and data quantity as well as why that might be the case. But still, their very detailed way of tracking elements of a climb is still very useful and worth consideration. Now going back here, we also have Stanford University conducted a study. And Stanford actually got around the data problem a little bit by using data from Moonboard. So Moonboard is a company that creates a standardized climbing wall found in many gyms. So they all have the same exact number of holds and types of holds, same exact wall angle. So it avoids a lot of these problems. And they also have a huge database of climbs created by the community and also graded by the community. So as you can see here, they had a database of routes that had 13,871 climbs in it, which is pretty useful. And they applied a variety of machine learning models, including a naive Bayes model, which is similar to what I did. And unfortunately, again, their accuracy was not what they were looking for. So they're around 35% for most of their models here, which is certainly not ideal. But it was a good idea to use, I think, the Moonboard data set for sure. So lessons to be learned from both of these, but clearly they are missing something. It's not enough on its own, what they're doing. So going back over here. Going on to the next slide. So for collecting the data, it was important I only used one climbing gym, first of all, to ensure that my data is consistent. After all, the entire reason for this project is that grades across climbing gyms are very inconsistent. But the idea is that within one gym, as subjective as these grades are, they should be at least consistent with each other. So I collected data on a wide variety of variables. And I'll actually will show you them here. So, I've got number of handholds just in total, keeping track of that for each climb. These I did not end up using. Overall distance, which you'll notice is not something that either previous study looked at, because I realized both of them really just focused on just the types of holds and the number of holds. But I want this to apply, first of all, to a wider range of things than just the moon board, for example. And I also do want to see if we can create a better model. So we're looking at overall distance as one thing measured in feet. We also look at the wall angle. So 0 would be a perfectly vertical wall. 15, a little bit more inclined, more difficult. 45 is about the highest you're going to see most places, unless it's going into a cave. And so on and so forth. And then we've got the number of footholds, just a simple count. Total crimps. So for the uninitiated, crimps are just like basically edges that vary in size and angle. And I put this category here for easy pinches, different types of pinches. Jugs, objectively, the most easy hold to grab. It's basically as close as you can get to a handlebar. And there's underclings, which I did not end up using as a variable in my tests. And neither did I really use slopers. And shallow jugs, just slightly shallower jugs, not as easy to grab. And then you'll notice we have easy crimps, medium crimps, difficult crimps, and even extreme crimps. And so the reason for this is, like I said, if you look at total crimps, this is just all of the crimps that the climb may have. And these are the different categories because crimps can vary quite a lot in angle and size, which I believe is important. And so these are categorized by angle and size, and we will look at that later, specifically how I split them up. And ideally, variables like slopers and pinches would also have all those categories, but due to time constraints, I was not able to do that. And so slopers and pinches were unfortunately somewhat omitted and had to be kind of absorbed into the categories of either crimps or jugs for my model to work, which is a little bit unfortunate and probably creates some issues. And then at the end here, we have the given grade for the climb, right? Whatever it happened to be when we collected the data on it. Okay, let's go back over here. So moving on to the next. So let's talk about how I actually did categorize these. So what makes a jug, right? So for the purpose of this project, I had to decide on that range of measurements. And the way I did it was I basically went around at the climbing gym and chose holds that I felt were jugs, for example. So very subjective, of course. And I took measurements on all the holes I decided were jugs. And I put this all in an Excel file and looked for a pattern and found one. And it was really as simple as that. So it started out subjective, but we found a pattern in what I thought should be a jug and used that to come up with these categories. So greater than or equal to 1.7 inches, but then also less than or equal to 45 degrees. So just for reference, the bigger it is, obviously the easier it is to grab. And generally, the lower the degrees, the more in-cut it is, the more you can scoop your hand in. And I also had a subcategory of jugs, shallow jugs, so just a little bit more difficult to grab than your standard jug. Again, it is worth noting that I would have done this for more things than just jugs. I mean, I did this for the crimps, right? Like we just talked about, easy, medium, and so on. I'm not showing you the ranges for these to save time, but I did do that. And again, I would have preferred to do this for the pinches and the slopers as well. Did not have time to do that, unfortunately. Now let's look at the data set. So we've got 25 observations in total. And just looking at the distribution, just of grades overall, we've got a bit of a right skew. And this is partially due to there just being less climbs in the higher grades at any gym. But mostly because I prioritized collecting data on the lower grades at first, because I wanted to get a model that actually worked on that consistently before moving on. And so I ran out of time collecting data for climbs V4 and up. So beyond that, though, the spread is pretty normal, especially given the relatively small amount of observations that we have here. So I looked at the distributions for any variable that was going to add to the model, and I decided to start out by looking at the jugs, right? Now, jugs are inherently the easiest hold to grab, right? So you would expect to see the amount of jugs generally decreasing as the grades go up, right? If they're easy holds, then you shouldn't see them on harder climbs, is the idea. And as you're about to see, the charts pretty much show that, starting at V0, right? We've got, 11 to 12 jugs pretty much is the standard. V1, it's centered closer to 9 jugs. It's a bit of a spread, of course. V2 clearly centered much lower. Some of them just have none at that point, but average is around 2 or so. The median is around 2. And then V3 again, most of them just don't have any jugs. And V4, just no jugs at all. It's worth noting I only had 2 climbs in my data set that are V4, and beyond that I barely had any, so I did not bother including them, as you can see. But overall, we've got a pretty good relationship with jugs and the difficulty of the climb, right? And I also looked at, other variables such as like total crimps, and that pretty much worked the way you would expect, more crimps as the grades go up. Number of footholds was similar to jugs. You get more feet to step on when you're on lower graded climbs. I'm not going to show you all of those, but the relationships were exactly as you would expect and helped inform my decisions and what I would use in my early models. So moving on, here's my initial model. So my initial model applies Bayes' theorem for something along the lines of a maximum likelihood classification. I just showed that the jugs variable has a strong relationship, right? And I checked the footholds variable. And looking at this two-way table, for example, you can get a sense for how my model works, right? So first of all, due to the small amount of data, I did have to bin the variables for the model to work as intended. So for example, if you look, the rows are labeled footholds binned, right? And the column is unlabeled here, but it's jugs binned. So for example, we look here for V2s, this is a table that represents just all the V2s in the data set. There are 5 V2s, 5 climbs that have a small amount of footholds and a small amount of jugs. So that's what that means, right? And yeah, so for example, if we were to test this right now and if we gave this model a small amount of jugs and a medium amount of footholds, the model would give you a 50-50 chance as either V2 or V3. And in this case, it was actually, this is an example of a V3 that I tested it with. So you can see it's not perfect by any means. And that's just because, a lot of reasons, but mainly we just need more data so we can have smaller bins and less overlap, right? I also did test this early model just at the local climbing gym with some climbs that weren't part of the data set. And those generally yielded a little bit better results because as you'll see in a little bit, I just don't have enough data to split it into a training and test set. So I can just take out one thing and test it, but even just one data point taking it out can actually have a pretty significant effect in the overall effectiveness of the model, right? So moving on from that. Okay, so every other related study, as we saw, focused almost entirely on the number and types of holds. So one thing I wanted to do differently was consider other variables, such as the wall angle and total distance covered. I have not used these variables as of yet, but I did look at them to see if there were any obvious relationships with the climb's given grade. Starting with wall angle, I took a look at each grade's distributions. And as you can see, like for V0, we've got most of them are around 0, which is what you would expect to see because that would be vertical and about as easy as it gets. V1, it's a bit more varied, kind of all over the place. And for V2, honestly, not that different from V1. A little bit more in some places, but not that different. And again, V3, there isn't really a whole lot to look at. And I actually stopped at V3 because beyond that, I have so few observations, it's not really worth looking at it. So, as you can see, there's really not much of a relationship here. And actually, it does make some sense, since even though a higher angle definitely makes a climb harder, it can be easily offset by just having more jugs, for example. So, you could have like a V1 that's on a 45-degree angle, but it just has way more jugs than a different V1 might have. So for now, I unfortunately cannot really fit this into my model, but some more research might yield some interesting results. Who knows? I also looked at overall distance, and since it's a continuous variable, it made sense to put it on a scatter plot. And again, unfortunately, there's not really any significant relationship that I could see here. The only thing I've noticed the outliers in the higher grades, but that makes sense given how much more difficult they are and how few of those climbs I have in the data set. It really is nothing of note. But maybe with some more data, we could see something here. I am hopeful. But moving on to the revised model. So eventually I managed to revise my model to support just about as many independent variables as I could want. So first of all, I did test for independence using a chi-squared test of independence at a significance value of 0.05, just to make sure variables that we're putting in here don't interact with each other. And beyond that, I just used logic combined with my climbing knowledge to select 4 variables that I thought would be helpful for this initial version of the revised model. So this new model has better code. It's much more easily formatted and easy to read. And I made a simple command line UI to make it easier to use, which you can see here, just a little welcome message, lets the user know what they need to input and lets them input it there, as opposed to inputting it in manually into the code how it was before. And this new model includes the higher grades, unlike the other one. So it does go up to, V0, V1, V2, up to V10 basically. But again, with those higher grades, it honestly, adding it into the model probably made it worse, but I just wanted to add it in. And once we have more data, it will actually prove more useful. And so how accurate was this model in the end? Well, it basically ended up being a little bit worse than the previous model. The previous model ended up, as you saw, I didn't show you too many examples of me using it, but it ended up being fairly okay for the lower grades, those V0 to V3. This model, as you can see, is all right. It's for V0, it pretty much correct. It was correct for the 2 times I tested it. If you're wondering what these tests actually mean, again, I couldn't actually split it into a training or test set without severely compromising the model. So I just opted to remove one climb at a time to test it and see how accurate the model is. And what happened here is these are 2 different climbs that I put in, even though you can see the results are identical. It's just that they both happen to fall into the same bins. And so that's what we got. And, you could look at, I tested V1 twice and, it got it right in the second try, but the first time I thought it was a V0. So it was within 1 at least here, but still, it wasn't correct. And then V2, it guessed incorrectly both times. Both times it seemed to think it was closer to a V3, which is interesting. Actually, sorry. V2, it was correct here. And then, V3, unfortunately, it was not very close to guessing that correctly. But again, when it's wrong, it's always at least guessing one of the grades right next to it. So that's something. And then I threw in 1 test for the V4s, and I didn't bother testing anything beyond that because it would be so inaccurate. And for V4, I mean, hey, 53% chance of being V3. At least it wasn't saying it's a V0 or something. But, with only 2 observations for V4s, it's to be expected that the model would not be very accurate. And again, if we had more data, we could also reduce the bins, and all of these would be more accurate because, again, these are all based off like small, medium, large. It's not using the raw data. So in the end, I created a somewhat decent model, I think, for lower grades and a very poor one for higher grades. The good news is I know some immediate and relatively simple ways to improve on it, starting with adding a new feature, proportions. A problem I ran into when testing my model in the real world was that climbs vary in numbers of holds. For example, a climb that consists only of 5 crimps may appear to have a small or medium number of crimps to my model. But if the climb has no other holds, the model won't take that into account. In reality, a climb with 5 crimps and nothing else is much more difficult than a climb with 5 crimps and also 5 jugs, for example. Instead, my model should use a proportion of number of crimps over total number of holds to avoid this problem. This could probably apply to most of the other variables as well. Yet another aspect to consider is the model itself. I had the opportunity to interview an experienced statistician who works at a test-making company called Cognia named Michael Finger. We talked at length about my dataset and possible ways to improve on my model. He recommended I look into latent class analysis, which is similar to maximum likelihood, but it will likely perform much better once I have more data. Frankly, I need to research it a bit further, but it looks worth checking out. With that, I'm wrapping up this presentation, and I hope it was informative.